As you see, I'm working in the physics department, so my physics colleagues say I'm a mathematician, but perhaps for you I'm a physicist, I don't know really. But in my title, you see there's Calogero-Moser-Ruijsenaars systems and some other concepts, Solitons and quantum fields. We heard already quantum field theory has been a good source for conjectures in the topic of this conference. But I'd like to perhaps say some things. There is also some things in quantum field theory one can make mathematically precise. And for me personally, so Ruijsenaars has played in my research a very important role. When I did my PhD, I finished around 1990. I studied papers of Simon Ruijsenaars in great depth, in great details, but these are not the papers that were mentioned by Halmer before. These were papers on quantum field theory. Simon Ruijsenaars actually, before he discovered these models in '87, he worked on constructive quantum field theory, and one of the motivations was he had a research project at the time. He wanted to construct a quantum field theory known as quantum Sine-Gordon theory, a quantum version of the Soliton equation, Sine-Gordon equation, and there was a physics paper proposing that this theory was equivalent to another quantum field theory, massive Turing model. And Simon Ruijsenaars realized that in order to, so his ambition was not just to make mathematically precise this quantum field theory, he also wanted to solve it. And he had some method which was very different from other people at the time working on this type of problem. And he realized in order to achieve the goal, he needed to get his hand on certain special functions, which at the time didn't exist. So he found a certain shortcut to make these functions well defined and kind of try to construct them directly. And I think this shortcut is what is known as Ruijsenaars systems now. And when I studied the paper of Simon Ruijsenaars, I didn't know all these type of things. I became close to becoming a postdoc of Simon Ruijsenaars. I had the privilege at the time of choosing my postdoc. But when I visited Simon Ruijsenaars in '91, I realized he was no longer interested in quantum field theory at all. So therefore, I made a different choice, continued working on quantum field theory. And then later on, strange enough, these tools I learned from Simon Ruijsenaars' papers turned out to be very useful in many different types of projects, physics projects, and so on. So all of this was based, much of my work was based on things I learned from him. And at some time around 2000, I got interested from a different reason, fractional quantum Hall effect or something like this, in Calogero-Sutherland type systems. And I don't know why, for some reason, I learned some things there. I realized that quantum field theory methods were useful to construct the known eigenfunctions of the Sutherland model, and these are the so-called Jack polynomials. And I don't know why exactly, I don't remember exactly, but somehow I realized, okay, elliptic case, there were things to be done, and I used my things I knew about quantum field theory to essentially construct a tool for constructing the eigenfunctions of the elliptic Sutherland system, Calogero-Sutherland system. This was this kernel function, Jan already mentioned this, that came out of this quantum field theory, and I think I presented this was 2001 or something. I met Simon and Ruijsenaars at the birthday meeting of Calogero, and there we talked about this. And then I spent some years on trying to use these kernel functions to construct these elliptic generalizations of the Jack polynomials. It was a very nice problem with a lot of functions. And in then I did other things for many years. And in 2018, I visited Japan, and I met Shunichi-san and Masayoshi-san Nomi, and they were interested in constructing the eigenfunction of the elliptic-Ruijsenaars model. I had learned about them before. Martin Halnes did his PhD with me, and he somehow then, for some reason, started working with Ruijsenaars, and I had some projects, and I had learned some things about this. And when I visited Japan, we talked about the Ruijsenaars systems, but then I remember I was living in Kobe, and Shunichi-san came, and we went up the hill to Kobe University. We had a very nice walk, and then Shunichi-san asked me a question, and I wrote it here. He asked me, do you know the Soliton equations related to the elliptic Calogero-Moser-Ruijsenaars system? So I didn't understand the question at first. Somehow I had blocked out the relation of Soliton systems and Calogero-Moser-Ruijsenaars system. This was something known to some degree, but I did not know about it. Elliptic Calogero-Moser-Ruijsenaars system, this is this non-relativistic version of the elliptic Ruijsenaars systems. I write it down for you that I make it precise. So for a physicist, you can think of that is just a quantum mechanical Hamiltonian of n particles which move on a circle. So there's periodic boundary condition somehow. And then you have a very particular two-body interaction. This two-body interaction is given by the Weierstrass elliptic B function. So my conventions are, I have a period, a half period, small l. So the circumference of the circle is 2 little l, and then the other half period, for some reason, is I delta. I want the second half period to be purely imaginary. So that is just the problem, and this problem I've worked on, and which is somehow related to a conference. So here, relativistic generalization, that is even one more parameter, but that was the type of thing I had worked on. And Shunichi-san's question was, what is the Soliton relation related to this elliptic Calogero system? So this question was for me extremely important, because somehow it made me realize that different research projects I had over the years were in some sense the same research project. So it was a very strange experience for me. It reminded me of a story I'd heard a long, long time before, when, namely the story, you know, of this, of the elephant story and blind men. So there were, I'm sure you all know this story, right? There were 5 blind men. They wanted to explore a certain object they didn't know, and everybody kind of touched this object somewhere, right? And then one of them said, oh, this object is a rope. The other one said, oh, it's a wall. And the other one, everybody said something different. And what it was an elephant, and depending on where you looked, you get totally different impressions of this type of thing. So I had exactly the same type of experience, and I thought, okay, I had different research projects in my years, and depending on what research projects I had, I was looking at something different, but in the end I was always looking at the same thing. And this same thing is a certain quantum field theory, and this quantum field theory is related to Soliton equations. So, and what I want to tell you in my talk is essentially tell you about this elephant, right? So what is it? It's a certain quantum field theory, and I think I talk about it now, since essentially this quantum field theory has been a source for nice conjectures for us. So when Shunichi-san asked me this question, I started a project with a young colleague at my university, Jonathan Lenels, and a common postdoc of us, Björn Bernson. And we wrote, after this, 8 papers, so it was extremely productive, and I will show to you why, because it essentially, just understanding this, we were lucky. The answer to Junichi-san's question was a Solitons equation? There was one, but this Solitons equation was not known before. So suddenly we had lots of things. So that's why we wrote several papers on this. And this I want to understand to you, and my ambition is perhaps I try to communicate to you how physics intuition is useful for coming up with good conjectures about interesting things. And a few lessons I learned myself, where I had kind of in basic things about Calogero systems, I missed a few very important lessons which I have learned on the way. And these perhaps I will try to share with you. Let's see if I can change this. So the plan of my talk is, so the topic is Calogero-Moser-Ruijsenaars Toda systems. I learned from you, if one mentions Sutherland, one should also mention Toda, because the original paper of Sutherland studied 3 models, and one of them was Calogero, the second Sutherland, and the third Toda, and Toda was first. And it's the specific topic related to the conference is the elliptic Calogero-Moser system, quantum version of it. Some things I say are also related to the classical versions of this. So I will try to tell you a little bit why Solitons equations have something to do with it, and perhaps also give you some simple physics intuition about this. And then I show you how this quantum field theory led to this new Solitons equation and what it is. And I will see how far I come. And in the end, I would say what it now seems to. So Junichi-san, Masatoshi-san, and I, we continue working on quantum field theory related to the Ruijsenaars system. And my outlook is in the sense, I believe what we are trying to approach is we are going back to Simon Ruijsenaars' original motivation. So perhaps at one day this circle will be closed. This original project of Simon Ruijsenaars, it looks like. We will see. You can judge yourself. All right, so let me just try to tell you why Junichi-san asked me this question and what was known before. I didn't know this, but this was known before. So the limit, the trigonometric limit of the elliptic Calogero-Sutherland system is the Sutherland model. That was the model which Sutherland described. And let me draw a picture to say what this model describes. So you can think of this as particles on a circle, right? Circumference is 2L, so x is identified with x plus 2L, periodic boundary conditions. And the classical picture is you just put an arbitrary number of particles there, right? And they interact with an interaction which is 1 over this distance here along the circle square. This is this 1 over sine square interaction which is here, and they repel each other, right? So that is the classical model. You have a very simple intuition. And now it's known since, I don't know, quite some time, that this model is related to a Solitons equation known as Benjamin-Ono equation. So this is a topic, perhaps, I will recall some basic things you need to know about it. Solitons equations exactly solvable nonlinear equations. And I write down this Benjamin-Ono equation. So the first 2 terms look very much like KdV equation. So it's a nonlinear equation for a function of 2 variables, x and t. X is position, t is time, and you have this nonlinear term. And the last term, I will explain to you that if you haven't seen before, a good way, a simple way to think about it. But I just write down this equation, and I'm telling you, okay, so how is a physical intuition that one can imagine that in this system there's a relation to the Solitons equation? So this is, you could think of a simple way to see a relation and have an intuitive feeling that such a relation is possible. and it is possible, that is something which is understood in a mathematically precise way, is, okay, think about this model in a classical way. You can imagine that you can, if I have lots of particle pairs, I can place these particles at equal distances, and a lattice constant, which is the circumference divided by the number of particles, right? And you can imagine that this is an equilibrium position. If I put the particles there, right, they will just sit there. They repel each other, they try to stay away from each other as much as they can, right? So this is a stable type of configuration. And now what I can do is, I can just excite the system and push, say, this particle here. I pump locally energy there in a particular way. And what has been shown mathematically is it's possible to excite locally the system in such a way, and what one has to think about it is, I try to make a limit when the particle number goes to infinity, and then you can imagine that the whole system behaves like a fluid, that I have a fluid dynamic description of this. I can write down an Euler equation for this, right? A hydrodynamic equation for this, and this has been done. You can formulate a hydrodynamic description of this Sutherland model, and this is a system of nonlinear equations, as a particular hydrodynamic description, and this hydrodynamics inherits the exact solubility from the Calogero system in a sense. So there is some integrability there. And this is work, recent work, a person I mentioned is Wiegmann, Pavel Wiegmann with collaborators and so on. And somehow out of these hydrodynamic equations, you can describe that you pump in here energy, and what happens is this local pump of energy actually will form a particular shape and will move there with constant velocity depending on how much energy you put there. And then if you have two such local interactions, then they behave exactly like Solitons. The typical thing, if they're far apart, they are individual energy packages, and if they come close together, there's interactions, and then they behave particle-like thing, like typically in Soliton equations. And this picture here, one can make precise, is understood, and is a good thing to have in mind to understand how, kind of on a classical level, you can imagine that this type of Calogero system is related to a Solitons equation. All right. So now to Nietzsche-san's question. As a preparation, there is an expected answer to Nietzsche-san's question. There was an expected answer. I didn't know that. I had to learn that from the literature. And now let me tell you what I learned from the literature in a nutshell, a little bit about Solitons equations. Okay, there is actually a Solitons equation which is called intermediate long wave equation. And that is an equation that depends on this parameter delta. That's the reason why I choose this parameter delta for the Calogero system in this way to match the conventional notation in this intermediate long wave equation. And I have written it here. It looks a little complicated, but you can think of this as an elliptic integrable system since you see here you have in this equation, instead of a Hilbert transform, which is an integral operator, you have this T operator, which is also an integral operator, and here you see the Weierstrass theta function appearing. So somehow you can think of this also as an elliptic integrable exactly solid system, and this potential in the Calogero system can be obtained by differentiating this function in the kernel. So here superficially you can imagine there could be some relation, right? So this equation was known. It's known as the Solitons equation, and the natural guess would be, okay, in the limit delta to infinity this reduces to Benjamin-Ono equation, and the natural guess would have been this is the Solitons equation related to the elliptic system. But this expectation turned out wrong. And here I just wrote some background to put this into perspective. So a simple way of thinking about all these equations, so everybody knows KdV equations, I've written it here. And KdV, Benjamin-Ohno, and ILW equation, they belong to something which I call chiral soliton equation. Chiral, what I mean by chiral is, you know, everybody knows KdV equations. If you have solitons, solitons move only in one direction, left to right, for example, right? So solitons, there's only, so if I make a parity transformation, changing x to minus x, I get a different equation. So that's essentially it. So it's not parity invariant, and the same is true for Benjamin-Ohno and for ILW equation. And all three equations you can think about, okay, you can get them by starting out with the one-dimensional wave equation. You look at the right mover in the D'Alembert solution, right, and then you add the nonlinearity, namely this one, to it, and then you add some dispersive correction, right? And KdV, your dispersion relation in the dispersive correction is K3, odd function of K. In Benjamin-Ohno, the dispersion relation is K squared, but you want the odd function, so you multiply K squared by sine of K. And that's exactly the Hilbert transform. Hilbert transform corresponds in Fourier space multiplication with sine K times I, right? So, and ILW equation is you change the dispersion relation to what is here. So it's a cotangent hyperbolic K delta K squared, and you subtract this thing. And then a way to think about ILW equation, that's a soliton equation interpolating between Benjamin-Ohno for delta infinity and KdV for delta going to 0. This KdV limit is a little delicate, a little tricky, but all this is well understood. So here, small little crash course about a different subject, but related to system. Now, why did Kenichi-san ask me this question? The reason was, as I told you, that I was interested in the elliptic Calogero-Sutherland system, and I did this quantum field theory construction to get kernel functions for the elliptic Calogero-Sutherland system. So that was my intention, since I knew that if I had the kernel function, I could do something about constructing these eigenfunctions. And I have here in one slide the type of result I had at the time. So essentially what I did is I used the well-known setting of conformal field theory, and in that setting, guided by some physics intuition, by some physics heuristics which I used, I constructed a certain operator which I called calligraphic H3 for some reason, depending on the parameter nu. This parameter nu is related to the coupling constant of the elliptic Calogero-Sutherland system. Its nu is essentially the square root of this G, which I had in my Hamiltonian. And then the basic identity are right here. So in this quantum field theory, there's a certain vacuum state called omega, and then there's certain particular quantum field theory operators, in technical language vertex operator, one would call them. All this can be done in a mathematically precise way. And what is, you can take in this quantum field theory an arbitrary number of these vertex operators with different arguments x1 to xn. You multiply them, and the basic result was, if you commuted that with this quantum field theory operator, act with the result of the vacuum, it's the very same as acting with the Calogero-Sutherland, elliptic Calogero-Sutherland Hamiltonian on this very same thing. And, well, you can stare at this relation, but as I told you, if you have this relation, you can get out of this kernel function identity, and then this kernel function has a physical interpretation as a particular correlation function of this onion or these vertex operators, if you wish, right? And Shiraishi-san knew this, that I had done this work, and it was known that in the trigonometric limit, if you had this type of construction, which of course was known before, you could get out of this somehow the Benjamin-Ono equation. So it was kind of natural that if you just look at this object, you would find out what this corresponding Solitons equation would be. And so when Shinichi-san asked this question, we looked into this, we checked out in these formulas which I had. So what is the Solitons equation? It turned out I had not written the results in a good way. The result was kind of hidden. They needed to be rewritten in a different way. And the funny thing was the correct way to identify the Solitons equation was actually extremely close to physics and other physics projects I had done. So I should have kind of used things I knew from other projects and which I had not done. But when we rewrote this operator in this way, it became clear that the Solitons equation was a new equation, and this is one equation I would like to show you. So here it is. So the equation turned out that it was a relative of the ILW equation. So this integral operator T appeared in this equation, but different from the ILW equation and all the other Solitons equations which I mentioned to you, it is a non-chiral equation. It is invariant under swapping x to minus x. And the way this is achieved is you have two functions, u and v, and they are coupled in this particular way. So I write it down. I don't want to say enough. All I want to say is, okay, this quantum field theory contained this Solitons equation, and the Solitons equation is the one related to the elliptic Calogero-Sutherland system. It turned out this equation is exactly solvable in a very strong sense. So all results you want for Solitons equations we were able to find for that equation. So that explains why we had two papers on this. And there was a physics interpretation, so we wrote also a physics paper proposing a physics application of this thing. And perhaps to just give you an impression, this is not directly related to the conference, but just to show you what, how kind of you relate. There was a kind of a relation between the Solitons equation and the classical version of this Calogero system, in the sense that you could write down a particular n Solitons solutions of that equation, and this is by kind of generalized Boole ansatz involving Weierstrass zeta function, and then the theorem is if these poles satisfy the equations of motion of this classical Calogero system and some constraint on the initial conditions, then this ansatz gives you the n-Solitons solution. So there's an intriguing thing which I don't quite fully understand. So we had used this quantum field theory, and from that got a quantum version of the Solitons equation. If you know this quantum version, you immediately guess what the classical corresponding equation should be. And then somehow the Solitons solutions of this classical equation are given by the dynamics of the classical Calogero system. So somehow what you have on the quantum level mirrors what you then can get on the classical level, and this is something we check directly without reference to the quantum system, since that's much easier, but I'd like to understand this more directly and see whether this can be understood more. And that was very useful, and the reason why we wrote other papers is that we suggested to every Calogero-Sutherland type system, and I think also Ruijsenaars system, there should actually exist the Solitons equation, and we got encouraged there might be Solitons equations that were not known. And it turned out to be the case, so we found there is certain spin generalizations of Calogero-Moser-Ruijsenaars type systems. This also exists for Ruijsenaars systems. I think Yun has done work on those. They are now started to being explored. In the Calogero-Sutherland case, there has been much more work on these spin systems. And sure enough, there's a Solitons equation, which I just wrote here. And we were also able to generalize that to elliptic case. So that's a Solitons equation for a matrix-valued function. And it's really different from what you would guess from the standard Benjamin-Ono equation, since you have a commutator term which disappears in the scalar case. And that actually is interesting from a physics point of view because that Solitons equation would perhaps describe the transport of spin. So there is quite some room still to understand this better. So I just wanted to show you that quantum field theory results are a great source for conjecturing interesting results. Here was one thing that was also explored in some. I show this to you since this is something where I have not full understanding, so it's kind of very strange. So the heuristic recipe to finding Solitons equations is Benjamin-Ono equation has this Hilbert transform in it, and the key feature of the Hilbert transform is that it squares to minus identity, which is obvious because in Fourier space it's multiplication to the sine functions times I. So it's manifest very easy. In ILW equation, this operator T does not square the minus identity. And that makes ILW equation much harder, much more difficult. Actually, what we found is somehow related to an integral operator which squares the minus identity. But this integral operator is actually a 2 times 2 matrix operator. That's it. So the whole thing is a little bit like what Dirac did, right? Going from the wave equation to the Dirac equation, linearizing and then somehow, so I don't fully hear is, so why does this square minus identity? The reason is that in Fourier space, this matrix, and you easily check if you square that, you get minus 1. I forgot the I here. So this thing squares to plus 1, if you multiply that by I, you get the minus 1. And it turned out that was heuristically there was a kind of rule which we had, and that was a master thesis and so on. Take any Solitons equation where the Hilbert transform appears, and then somehow replace this Hilbert transform by this matrix operator in a clever way by doubling the degrees of freedom. In all examples we looked at this work. So that's the reason that there were several papers. All right. So another result of this, out of this quantum field theory, and that is for me interesting subject. So as you know, Oleg is here. He found first that the Calogero-Sutherland type systems have generalizations. They called it deformations. I think of it more as a generalization of the Calogero type system where you have 2 types of particles, and the numbers of particles n and m of these 2 types are arbitrary. And so if you have the standard Calogero-Hamiltonian, you get this deformed Hamiltonian by having the coupling constant G, and then adding the Hamiltonian for an arbitrary number m with positions x tilde, I call them, with coupling 1 over g with this coefficient minus g, and then you introduce interactions between these particles xj and xj tilde. So this is a generalization of the Sutherland Hamiltonian, which from a physics point of view is not so natural. But it turns out, if you look at the quantum field theory version of the system, then you kind of get this automatically. It's an extremely natural object. Actually, in this quantum field theory of the elliptic Calogero-Sutherland system, you get a 4 variable generalization, which we call generalized elliptic Calogero system. So you have this deformed Hamiltonian, but then actually you have 2 copies of them, x tilde, y tilde, all the particle numbers are arbitrary, and then you introduce particular interactions which are written. And this is something, a small thing, why is the hyperbolic and elliptic case different from the trigonometric case? I think that is a very basic message. Ruijsenaars always said, okay, quantum sign-Gordon is related to the hyperbolic Ruijsenaars system. The way I think about the elliptic case is, it's the hyperbolic system, but then hyperbolic system on the real line, but then quantum field theory on the real line is difficult. I have what physicists call infrared divergences. So in order to regularize these infrared divergences, I replace my real line by circle. And then I get the elliptic system. And let me show you why this is really different from the standard trigonometric case. The reason is, if I have a two-body potential, V of x, which is some coupling constant, g squared, divided by sinh square pi over 2 delta times x. So that would be, and I'm thinking, and probably I should put here also 2 delta x squared. The reason why a system with this type of interaction is, from a physics point of view, really different. So if I have the potential pi over 2L squared, the trigonometric way is sine square pi over 2Lx. The good way of thinking about it is that this is a 2L variant of 1 over x squared. The original Sutherland system had interaction 1 over x squared. And I get this here when I periodize the 1 over x squared thing. And the precise formula is something like this. You know, I can write this sum of all integers 1 over x minus 2ml squared. Right? Mittag-Leffler series or something for 1 over sine. Oh, here I have sine. So this is sine, right? Now, sinh here, I can also write such, but here I have an imaginary thing. So I have not a direct geometric interpretation of what that means. But from a physics point of view, this interaction is very different, because this interaction decay 1 over x squared decays algebraically, right? Whereas this decays exponentially. So this is much more short range. And the elliptic case, I think a good way to think about it is, it's the 2L variant of 1 over sinh square. So 1 over sinh square is, to me, the most elliptic case somehow, which is hardest because here, if I look at this quantum mechanical Hamiltonian, in this case, the spectrum becomes continuous, and so I have scattering solutions, and this is quite difficult. So I'm thinking about the elliptic case as an integrable regularization of the hyperbolic case. And one very particular thing is, if I have the Calogero system with this interaction, what I can do is I can shift some of the particles to xj plus I delta, the imaginary half period. And when I do this, that's an old trick which Calogero already figured out in one of his very first papers, then I can write the Calogero-Hamiltonian as a system of two kinds of particles. The particles which are unshifted, they interact with 1 over sinh square. The particles which are all shifted amongst themselves also interact with this, but the particles which interact, the shifted and unshifted, they interact with minus, same thing here, cosh hyperbolic square pi over 2 delta x. Because if I shift that potential by the imaginary half period, my 1 over sinh square becomes cosh, right? So I can get right away integrable system of two kinds of particles where the two groups interact with these soft interactions, and actually that's what you get here. And if you look in the early papers of Ruijsenaars, he also says if you want to understand the quantum St-Gordon theory, you should actually look at this generalized model, but actually I think what one should look is this generalized model which you get by doing the combination of the deformed model and then doing the trick of doubling the degrees of freedom even more. I should say there is a generalization of this to the Ruijsenaars case, which I think we wrote in a paper with Farrokh Attai, who is here, and Martin Halnes a couple of years ago, where we had some results in this direction. And the reason we could write this was essentially, yes, it was easy to guess if you knew it here, it was kind of easy to guess what it should be in the relativistic case. But at this point, I don't have a quantum field theory version on this. So I thought, how much time do I have? 5 minutes. Okay, this is perfectly enough. So I think the reason I choose to talk about this is that what happened was, okay, there was this quantum field theory paper, so what was done there was mathematically precise, but then when we revisited this, we got these projections about Solitons equations, which we just took and worked on without trying to make sense of the quantum field theory, but then we had a project which took quite a while and which we finished this year in February, I think it was, that we make the quantum field theory construction precise. And the funds, and let me just give you 3 slides on this. I don't want to say too much on this, just a little bit on why I think there is a chance that this kind of gives some clues of perhaps going back to Simon-Ruijsenaars' original project. A fun thing, I told you a little bit the story about the elephant. In research projects which I thought were totally unrelated to this thing here, and where I just thought, okay, the conformal field theory methods were used also, but otherwise I saw zero relation between this type of thing. I studied a model which in condensed matter physics is known as Latinger model. So Latinger model is kind of, in some way there is a relation. A particular case, a limit of the Latinger model is the massless steering model. So I mentioned massive steering model was a project of Ruijsenaars. If you set the mass to 0, this model is understood since the 60s. So the hard thing in this quantum field theory problem is actually that you have the mass, but without mass, the technology of solving this was already discovered and found in 1967, and there's a famous paper by Elliot Lieb and Mattis solving the so-called Latinger model, and I've worked on this and used it for different types of things. But the amazing thing was, what helped to rewrite this quantum field theory construction I did a long time ago was, we understood it was exactly a particular case of the Latinger model that you were sitting behind. So the quantum field theory you had is the very same for this physics model. It's just a particular case, and that gave exactly this Calogero-Moser-Ruijsenaars transformation, you know what that is, that was needed to get into the game in order to get the elliptic functions. So that was for me one thing that somehow in work I did on the Latinger model, I kind of also worked on this particular problem. So that was a very strange thing and kind of a cute thing. The other thing was, and that thing we had came out in the end, I show it right away, that this operator, which I call the second quantization of the elliptic Calogero system, could be written in this Latinger Fock space and so on, exactly like a physicist would write down a Fermi variant of particles on the circle. Here the first term is exactly the standard kinetic energy in a quantum field theory language, dispersion relation, second derivative, non-relativistic fermions, and you have density-density interactions exactly with the Weierstrass elliptic function and the shifted Weierstrass elliptic function. And you have 2 kinds of fermions, rho plus and rho minus, which have the interpretation of left and right going fermions. So physicists call this a non-chiral quantum field theory, since you have degrees of freedom moving to left and right in a symmetric way. And that object, which I wrote in a very different way, could be exactly written this way. So if I would have trusted physics more, I could have written it down directly, but I would not have dared. So this came as an afterthought, much, much later. But from a sense, this would be exactly what you would tell a physicist in the first introduction of the talk, and physicists would right away recognize this. But there's a technique called bosonization, and then this looks like this. So you can express this Hamiltonian in terms of the densities only. And when you write it like this, then you see immediately, if you have the Heisenberg equations for these densities and rescale the variable, you get exactly this quantum version of the non-Caroline W equation, which we call. And you see immediately a physics interpretation of these degrees of freedom. And this generalized model came out since this operator right away provides a second quantization of the generalized elliptic Calogero system, because what I considered then, 20 years ago, was only one kind of vertex operators, but there's four, and all four of them are on equal footing, and there's a symmetry there, so you have the left and the right moving degrees of freedom, and then you have a certain duality for this parameter nu going to -1 over nu, which is manifest in this construction. And sure enough, if you can take arbitrary vertex operators there, and if you do this, then actually you get right away this generalized Calogero-Moser-Ruijsenaars system. So I think my time is really up. I wanted to share with you that quantum field theory is useful as a setting, giving you interesting conjectures in context of the topic of the conference, but also relating it to solitons, and in some way, eigenfunctions which we are looking at in some sense, which I don't precisely understand and would like to understand better, is related somehow to the soliton theory. In a way, I would like to understand better. Right now, I cannot do this. I showed you this soliton equation and other soliton equations we found in this way. I think one important message is that we use these kernel functions to construct eigenfunctions of the elliptic Ruijsenaars system. But I think if you want to use these eigenfunctions to construct this quantum field theory, what Simon Ruijsenaars wanted to do, one should actually generalize this to the generalized elliptic Calogero-Moser-Ruijsenaars systems. And this is really a project where one has to start from scratch. So what is known right now, so that is, I think, a huge project which I think would be interesting to do. Because, but that is quite some work. So these generalized models are of interest if one wants to use these eigenfunctions to solve some quantum field theory. And I'm now trying and thinking and learning from Solitons this Q-deformed CFT providing quantum field theory construction of the Ruijsenaars systems. And somehow I have the feeling that this perhaps might help one day to solve the original problem this Ruijsenaars led to these models, namely making precise mathematical sense of quantum Avoidance fields and massive theory models. Thank you.
Questions? Thank you for a very interesting talk. And, I want to check that this deformed Calogero model is also called a double Calogero-Moser-Ruijsenaars model, I think.
Oh, I'm not sure, but I think in the audience is people that can answer that question. Oleg, is it double? I don't know.
Yeah, so my question is that this is
supersymmetric.
Okay, so in that sense,
there's some confused. I think
this is related to the root system of super early algebra. So this is not yet the super, but anyway, this is related.
It's related to root systems of
super algebra.
Okay. Of super algebra, but there is also supersymmetric extensions of Calogero systems which are different, where you really have fermion degrees of freedom, Grassmann numbers.
Yes. And my question is that so for this deformed one, so there's this kind of interpretation from this root system. My question is it similar interpretation for the generalized Calogero system in terms of their system? Because this is
It's
more
a good question, and I have no answer to this. I have no answer to this.
Thank you very much.
Thank you. It's an interesting question. I know too little about truth systems.
Any other?
I'm just curious that is there some kind of any similar difference equations or some difference solid equation related to this kind of?
Is this right? Yeah, that is. I think there is proposals by Calogero-Moser-Ruijsenaars and the collaborator on a difference equation and the Q variant of Benjamin Ohm equation related to the trigonometric Ruijsenaars system, I understand. And yeah, the thing is, so here is a big thing in understanding that is like what is a standard local Solitons equation. So how could that be related? You would expect from Ruijsenaars system that it could be a Q Solitons equation. I don't know. Yeah, here's some big. I don't understand. It's a very good question. I don't know. How can you get something local? Yeah.
So you obtain quantum field theory corresponding to elliptic Calogero-Moser-Ruijsenaars model, and I was wondering how do you use your quantum field theory to solve the elliptic Calogero-Moser-Ruijsenaars?
Yeah, what it was is I just used this as a tool to obtain a kernel function for the elliptic Calogero-Moser-Ruijsenaars system, the simplest one. So that was my motivation for writing the paper. Later on, the strange thing was people were interested in this, so I presented this in Rome, I think 2001, Simon was also there. But then the people there all told me, oh, we don't want to hear about the quantum field theory stuff. That's not interesting, and then I worked hard to eliminate all quantum field theory examples through not using it. So in a sense, I had the impression nobody was interested in quantum field theory related to this thing, and only recently, therefore, I returned. So from this point of view, it was a total overkill. Now I'm kind of happy that it was useful for something else also.
Yes.
Maybe short question. Very nice. I was listening to your explanation, something in my mind. So this is about your color function identity with tau derivative. Maybe you are explaining this kind of stuff in your language.
Yeah, that is of course a very good thing. You're absolutely right. You get from this quantum field theory in general, that was related to in the elliptic case, can you have kernel functions going from n minus 1 to n? So that's a big question. And not for, I think, in the Calogero case, one can understand you can have such a kernel function for a generalization of Calogero, which is this non-stationary system. And I would very much want to know what this is in the elliptic case.
I think you are saying that in the differential setting, this color function is with which says particle numbers from n minus 1. Can you explain?
Yes, it comes out of the quantum field theory.
One small question. What about the situation in difference?
My hope is, I don't know how to do the elliptic quantum field theory, but my hope is it's worth trying to find it, because if one has it, one might find the answer there. But I don't know.
Can you extend your theory for D case, for D, not BC, not only for BC case, but for D case? For example, for D4.
I'm very interested, but I must say I know too little about the T case and I have not tried. So I don't know. And I have no idea how hard it is.
Let's start speaking again. We have the lunch break. Resume lunchtime. Resume at